In this video, I'd like to go over the topic of hydrogen bonding. All right. First of all, hydrogen bonding is sometimes misunderstood, and in my opinion, sometimes the misunderstanding can stem from the term hydrogen bonding. All right, and you see that part of the word involves the term bond. All right, and it would be very easy to assume that a hydrogen bonding is nothing but a covalent bond to a hydrogen atom. All right, but that's not what it is. All right, so right off the bat, let's get that straight. A hydrogen bond is not simply a covalent bond to a hydrogen atom. All right. Instead, what it is, it's a special type of dipole-dipole interaction between atoms. All right, between atoms that are not covalently bound to each other. All right, so first of all, let's review a little bit about what a dipole-dipole interaction is. So hopefully you can recall what polar bonds are. That's covalent bonds between atoms where the electrons are not shared equally. All right, and whenever you have this causes one of the atoms to be slightly delta positive and slightly delta negative. All right, and whenever you so an example of this would be something like acetone. All right. So between carbon and oxygen, the oxygen is the more electronegative, the carbon is more electropositive. That means that there's going to be a slightly negative charge on the oxygen and a slightly positive charge on the carbon. All right, we can designate those with the delta negative, delta positive signs. All right. Well, if this was the only molecule in the world, then there would be no such thing as a dipole-dipole interaction. But if you have any amount of this substance, it's going to have neighbors, all right? And its neighbor is also going to have those delta positive, delta negatives. And what ends up happening is that the delta negative atom of one is going to have a slight attraction to the delta positive atom of a neighbor, all right? And that's what you call a dipole-dipole interaction, all right? So technically a dipole is any molecule that has a slightly negative side and a slightly positive side. All right, so you have to have polar bonds for that to happen. All right, so a simplified way to think about this is just to think is wherever you have molecules where you can see an isolated polar bond, all right, the delta negative side of one is going to be attracted to the delta positive side of the other. All right, so as I said before, hydrogen bonding is going to be a special form of this. So a hydrogen bond is going to be an attraction between atoms that are not covalently bound. Notice these two atoms, this carbon and this oxygen right here, are not covalently bound to each other, but there is an attraction between them. All right. So one thing that might help out is if instead of you thinking of the term hydrogen bonding, you thought of the term hydrogen stickiness, because that's a more accurate description of what it is. It's a stickiness between neighboring atoms. All right. So again, these right here, these are bonds between. This is a covalent bond between an atom and a hydrogen, but this is not what is meant by a hydrogen bond. All right. So what is specifically a hydrogen bond? All right. Well, it is an attraction. This is going to sound kind of technical at first, but we'll go over it. All right, it's an attraction between a hydrogen that is covalently bound to a nitrogen, oxygen, or fluorine, which I'm going to abbreviate as NOF, and a lone pair on a neighboring nitrogen, oxygen, or fluorine. All right. Breaking that down. So first of all, there's several things that we need. First of all, we need a hydrogen which is covalently bound to either a nitrogen, oxygen, or fluorine. All right, so obviously it would just be one of these. So let's pretend that this is just a plain old nitrogen right here. All right, that would satisfy the first part of it, the hydrogen that is covalently bound to one of those atoms. All right, and we need that to be near another molecule that contains a nitrogen, oxygen, or fluorine. All right, and one thing hopefully you realize is that if you have one of these atoms, it's going to have a lone pair on it. All right, and that lone pair is going to be particularly attracted to the delta positive on this hydrogen. Right? Notice all of these atoms right here are more electronegative than hydrogen. All right, and what that does is it pulls these electrons in this covalent bond towards that atom, and that means that this hydrogen is going to have a slight positive charge. All right, so what the hydrogen bond actually is that stickiness between this atom, one of these atoms right here, to this hydrogen, and it occurs because of the attraction of that lone pair to that hydrogen of its neighbor. All right, so I just want to be clear about this. This should say stronger. All right, this little stickiness right here, it is definitely stronger than a typical dipole-dipole interaction. All right, so for example, we showed this dipole-dipole interaction right here. This is not a hydrogen bond, all right, but it is a slight area of stickiness between neighboring molecules. All right, so hydrogen bonds are going to be stronger than that type of an interaction. All right, but they're not going to be nearly as strong. They're much weaker than covalent bonds. All right, so these bonds right here, these are covalent bonds. This bond right here is much stronger. So this hydrogen is bound to whatever this atom is, much stronger than this one of these atoms would be attracted to this hydrogen. All right, so one analogy that I use here is to think of a covalent bond. Think of that like cement. All right, that like when you have a covalent bond, atoms are cemented to their neighbors. All right, some stronger than others. Of course, you probably know, like in acids and bases, the hydrogens can the bonds are sometimes they're easy to break. All right, so but if you just think of these as more like cement, think of hydrogen bonds kind of like Velcro. All right, and the reason that Velcro is a good analogy is that, first of all, it's not that strong. If you pull hard enough on it, you can separate the strands of Velcro. All right, but the other thing about Velcro is that even though you can pull it apart, you can also reattach it very easily. And that ability, the thing about these hydrogen bonds is that they can constantly be being formed, broken, and reformed again, and that's going to contribute to the function that they serve in between different molecules. Okay, so before explaining what is different about a hydrogen bond versus a regular dipole-dipole interaction, I want to just go and show the most common example of hydrogen bonding, and that's going to be what happens in water. All right, so hopefully you're familiar. Water is this bent triatomic shape right here, and if you have a bunch of water molecules around here, you notice that the way they arrange. You always have the delta positive hydrogen near the delta negative oxygen. All right, so that right there. Notice that this part of it right here, that serves that first requirement of a hydrogen bound to a nitrogen, oxygen, or fluorine. All right, so we've got that part of it right there, and that hydrogen is near a neighboring oxygen, nitrogen, or fluorine. And so if you just threw a bunch of water molecules together, they would naturally want to arrange so that this situation occurred. Much in the same way as if you just took a bunch of bar magnets and you threw them on a table. There would be certain ways that certain ends of some of the bar magnets would naturally want to orient towards the ends of other bar magnets. All right, it's nothing magical. It's just there's little areas of attraction that naturally occur. All right, and actually I should have drawn a dotted line right here. And notice hydrogen bonds are typically represented with a dotted line between atoms. You don't have to have, like if you're drawing molecules, you don't have to draw the dotted line, but if you do draw that dotted line, it's there to highlight the presence of that hydrogen bond. All right, so this one thing about the hydrogen bonds, why it's important to water, is it explains something very important about a property of water, is that it gives water an extremely high boiling point for a molecule its size. All right, by comparison, hydrogen sulfide, which is by comparison larger than water. All right, the only difference is oxygen versus sulfur. All right, water can hydrogen bond. Hydrogen sulfide can't, because sulfur is not one of those NOF atoms. All right, the boiling point of water is 100 degrees Celsius. The boiling point of hydrogen sulfide is minus 60 degrees Celsius, which is astounding when you consider that H2S is a larger molecule. And remember, because of London dispersion forces, the larger the molecule, the more it tends to want to stick to its neighbors. All right, so this guy has the advantage of being larger than water, but even with that size difference, water still has a tremendously higher boiling point, which means that the molecules stick to their neighbors much more than these molecules stick to their neighbors. And it's because of that property that water can extensively hydrogen bond with its neighbors. All right, so I mentioned that you can make the comparison of hydrogen bonds to kind of like Velcro. All right, so obviously if you have water molecules, these things aren't, pardon the pun, frozen to each other. All right, actually, if water is frozen, what happens is that these hydrogen bonds essentially become permanent. All right, but in liquid water, there's enough kinetic energy that these hydrogen bonds can form temporarily. They can get broken, and these molecules can reorient, and then like let's say that this guy rotates clockwise. All right, you can form a hydrogen bond between this guy and that hydrogen once this thing is rotated near it. All right, so these things are constantly forming, getting broken, forming with other atoms that they can do this with, and that leads to that sticky arrangement, but it's weak enough that these things can still move past each other. All right, so what's so special about a hydrogen bond that makes it different from normal dipole-dipole interactions? All right, the answer has to do with the fact that hydrogen does not only has one layer of electrons around it. All right, whereas if we take a look at this bond right here, remember the electron configuration for carbon. It would be 1s2, 2s2, 2p2. And we can see from this configuration that carbon has an inner layer of electrons, all right, that are not involved in covalent bonding. All right, so even though these electrons are pulled away from the carbon because of the electronegativity difference here, that the nucleus in this carbon atom is still going to have an inner layer of electrons surrounding it from that first layer. All right, so it moderates the amount of delta positive that this particular atom can have. All right, by comparison, hydrogen's configuration is 1s2. All right, so the only electrons that it has are its valence layer. All right, so when you pull these electrons away from hydrogen, there is no protective layer around that nucleus. All right, so there's no inner layer electrons, and I had my handwriting got chopped off here. Anytime you have a bond to an electronegative atom, it's going to leave the nucleus of that hydrogen relatively exposed. And what that allows for is a much closer interaction between this delta positive and a neighboring atom than you could with different types of atoms.